Okay, in this flipped lesson we are going to look at the third part, part C of the energy subtopic, and we're going to look at electrical energy. So firstly, what are the things that we need to learn about? Although most electricity is generated using fuels to drive steam turbines, electrical energy can also be generated using photovoltaic cells, known as solar cells, and directly from the oxidation of fuels using galvanic cells. And what you need to be able to do is explain the advantages and disadvantages of a direct electricity generation, i.e. photovoltaic and fuel cells, which are a form of galvanic cells, compared to using steam turbines. So steam turbines are what we would traditionally associate with being involved with traditional coal and gas-fired power stations. What happens is that basically the fuel, e.g. coal, is burnt in a combustion reaction. Obviously that combustion reaction produces a lot of CO2, which is a greenhouse gas. You also get oxides of nitrogen, which can contribute to photochemical smog, and the oxides of nitrogen and sulfur, which can contribute to acid rain, which are all potential environmental problems. That combustion produces heat. That heat is used to heat up water to make steam. That steam then makes a turbine spin around. That turbine then makes a generator spin around, which then converts that into electrical energy. So you can see there's lots and lots of steps in this process. Lots of steps basically make that, a very inefficient process. Where energy is lost at each step, it's an inefficient process, as I've just said. We also get the production of lots of pollution. So, if you like, that is the disadvantages of the steam turbine. I guess the advantages, which I haven't said here, is that coal and natural gas are in abundant supplies still, and they're fairly cheap compared to other fuels. So that's the reason that we make so much electricity using coal and natural gas and steam turbines, even though it's quite an inefficient process. If we look at how the photovoltaic or the solar cells work that are like on our rooftops and in various applications these days, they take sunlight and they convert that directly into electrical energy. So it is just a one-step process. We get the direct conversion of light to electrical energy, don't have all those steps where energy is lost. There's also no ongoing pollution, but we do need to remember that there is considerable carbon emissions from the production of photovoltaic cells. So once they're operating, yep, they save a lot of CO2 emissions, but we always need to remember that we need to use a reasonable, we produce a reasonable amount of carbon emissions in that production of the photovoltaic cells in the first place. The other type that we need to look at, which is the galvanic cells, which includes things like fuel cells that I'll talk about in a minute, and flow cells, which I'll talk about in a minute, is they take chemical potential energy and convert it straight to electrical energy. So they are essentially how a battery works. Obviously we have problems with a battery that it won't last forever and it goes flat. However, fuel cells and flow cells overcome some of those problems, and they are very efficient at converting chemical energy to electrical energy. So the chemical potential energy that's stored in our fuel, in a fuel cell or a flow cell, is nearly all converted to electrical energy. Whereas in this case here, this chemical potential energy in a fuel, where it's used to power a steam turbine, only a small amount of that gets converted to electrical energy. So again, that's the main advantage of these processes that have less steps. I think most of that stuff should hopefully be common sense. Have a look through and read some more if you need to. I don't exactly agree with how they present it in the textbook, but it does give you an idea. But I think if you understand it at the level I've explained it here, you should be able to answer any of the questions that you need to in a test or an exam. Okay, in this next slide, we are going to look at how a fuel cell works and how a flow cell works, and in particular one example of those. So just in terms of what are the things that we need to be able to do, fuel cells, including flow cells, are galvanic cells in which the electrode reactants are available in continuous supply. I'll explain what they are and how that happens. We need to state the advantages and disadvantages of fuel cells compared with other galvanic cells. That'll come in the next slide. We're going to identify the anode and cathode and their charges, as well as the direction of ion and electron flow in a fuel cell, given sufficient information. I'll show you that on the diagrams. We need to write electrode half equations for a fuel cell given sufficient information. So we did half equations in year 11, and I'll just go over some common half equations, and I'll probably steer you back to the year 11 stuff if you need to remember how to do that. And then we need to discuss the advantages of flow cells compared with other fuel cells. That'll come on the next slide, like the other advantages and disadvantages. So this slide's really going to focus just on how the fuel cells work and how the flow cells work. So what is a fuel cell? So the first key thing about a fuel cell is it is like a galvanic cell in that we have an anode and a cathode and an electrolyte. At the anode, which is oxidation, we get the loss of electrons. So electrons flow lost here, they go to the other electrode, the cathode. Reduction happens at the cathode, which is a gain of electrons. So we have that sort of inner workings being just like a typical galvanic cell that we would have looked at as a battery or something like that in year 11. Where they're different is that we can constantly put in the fuel and the air, or oxygen in this case, which is the most common oxidant that we would use, and that can be constantly replenished in the battery. So it's not like there's a limited amount of material for the anode and a limited amount for the cathode, and once that's all reacted, that battery is flat and either needs to be thrown away, or in the case of, say, a lead acid battery, it needs to have electricity applied to it to reverse those reactions, to recharge it up, to restore that chemical potential energy. What happens here, fuel can constantly go in, the oxidant, which is air, can constantly go on this side. So as long as we keep pumping fuel in to this galvanic cell, it will keep producing an electrical current. This is an example of a, I think it's called a PEM. I haven't written that down because I don't think you need to remember. Yeah, a proton exchange membrane fuel cell. Notice you don't really need to remember that, but you'll see that in the book. Because it exchanges hydrogen ions, which are protons, that's why it gets that name. So what happens is that hydrogen gas goes in, and at this electrolyte, the hydrogen gas gets converted to 2 H plus ions, 2 hydrogen ions, and we get the release of 2 electrons. So loss of electrons on this side, that's why it's oxidation. They go through the circuit to this one. Over here, the oxygen's coming in, that is reacting with the H plus, which is being generated at this electrode and moving through this membrane across here. And we get the formation of water, which is what comes out the bottom here. Oxygen goes in, water comes out. It's a gain of electrons, that's why it's reduction. So the overall reaction that's happening here is 2 hydrogen molecules reacting with 1 oxygen molecule to produce 2 water molecules. So this looks like a combustion reaction, the reaction of a fuel with oxygen to make water. However, we're not getting combustion, we're not burning this, we're not producing heat. This energy that's stored, this chemical energy that's stored in this fuel, is being converted directly to electrical energy without combustion and the production of heat, and then all the processes that need to drive turbines to make electrical energy. So that's our hydrogen fuel cell. Our flow cell is a little bit similar, but a little bit different. And the most common flow cell that you'll see is a vanadium flow cell battery. And what that has, again, is it has an anode here in blue, a cathode here. It has a a porous separator or a membrane between the two. where we can get the exchange of ions, like the salt bridge that you would have built in the galvanic cells that we built in year 11. Obviously we have the anode, so we have the loss of electrons here. I haven't drawn that in, I'll just quickly put that in. We have the loss of electrons at the anode because it's oxidation, and they go through the circuit like that to the cathode, where we get the gain of electrons, reduction, and that basically, that process is what drives the flow of charge. The way this differs from a usual galvanic cell, like a battery, is we have this storage tank of anode electrolyte, and then we have another storage tank of a cathode electrolyte, and those electrolytes are basically being constantly, well, let's do the blue one, they're being basically constantly pumped into this cell, so into the galvanic part of the cell. They're producing the current, and then the waste then gets pumped back through. This diagram doesn't have it, but some diagrams would show you like a separator in the tank like that, and then basically you would have the fuel down here and the waste down here being separated. And then basically, eventually, obviously, if that fuel gets all used up, basically you just pump out the waste from the tank, which can in some cases be regenerated. The book talks about how the waste is regenerated. I don't see that as part of the course, so I'm not talking about it here. But you can just then put in more, and I use fuel in inverted commas, so you put more of the vanadium fuel that you use in, and then basically the battery can keep going. So it's very similar in some ways to the fuel cell. These tend to use gases, so hydrogen gas is the most common, and oxygen gas, whereas here we have liquid electrolytes that can be easily stored in large tanks to operate it. So the most common one works with based around the vanadium ion, and we have vanadium 2 being converted to vanadium 3 with the release of an electron at the anode, so loss of an electron, oxidation, anode. That then, at the cathode, we have the VO2+, I think that's called the vanadate ion, but don't quote me on that, plus 2H plus an electron goes to form the VO2 plus H2O. So what you need to be able to do for these is write electrode half equations for a fuel cell given sufficient information. So the sufficient information would be like, what's the redox couple? So if I go through it for this vanadium one here, step 1, the redox couple you'd be given, that's if you like the sufficient information it's referring to there. Then you would balance out the oxygen by using H2O. So there's 2 oxygen on this side of, let me use my cursor. There's 2 oxygen on this side, 1 on this side, so we add a water to balance the oxygen. And then step 3, balance the hydrogen using H+. So we have 2 hydrogen there, so we've got 2 H+ here. And then finally, you've got to balance the charge using electrons. So here we have, forget the electrons in there for the moment, a 1 plus 2 pluses, so we have 3 plus here, 2 plus here. So to get 3 plus down to 2 plus, we've added that electron there. So that's from last year. That's just a reminder of that half equation method that you have to be able to do for these half equations given the redox couple, which is just sufficient information. It doesn't say you have to convert half equations to full equations. Remember, you've just got to make sure that the number of electrons that are gained equals the number lost. So that one is just a straight add up that reaction there and that reaction here. Here we have 2 electrons being lost, but 4 being gained. So that's why we have 2 H2 down here. We need to double everything in this equation when we add it to this to make sure the number of electrons lost is equal to the number of electrons gained. Have a look back over the stuff from last year if you're not sure about that. So that is our introduction to the fuel and flow cells. In the next slide, I'll go into more detail on the advantages and disadvantages of each. Okay, so if you read through the book, mine are slightly different to those. I think these ones make it a little bit easier to understand and clearer. The book's not wrong, but I think the way I've done it hopefully is easier to remember and fits better with the explanations. So the advantages, just get my cursor up, the advantages and disadvantages of fuel cells compared with other galvanic cells. And by other galvanic cells, we basically mean the type of batteries that we built and looked at last year. So the advantage is fuel can be constantly replenished so that they don't go flat. They don't run out of charge. We don't have to worry about them slowly getting flat near the end of their life because we can just keep putting in more fuel. Fuels such as hydrogen and methanol are in abundant supply. So there's large supplies of those sort of fuels. They're easy to make generally. The waste products removed during operation, so we don't have to worry about the build-up of waste and the cell needing to be, if you like, stopped to remove the waste. They basically, the waste can be easily removed. They also give us what means called a high energy density. So we talked about energy density with combustion. That means we can just get a lot of energy out of a smaller amount of fuel. The disadvantages, though, is they need high purity fuels. Otherwise, the electrodes are easily contaminated and the fuel cell won't work. So we need high purity fuel. High purity fuel means lots of cleaning and purification. That usually means it costs lots of money to make the fuel. They also require rare and expensive catalysts such as platinum to make these reactions happen, so that can impact on how well they work. There is also limited infrastructure for fuels such as hydrogen at the moment. We don't have we can't just go and buy hydrogen from a service station and so on. They're also, because they're a new technology, they're still relatively expensive compared to combustion engines that say run in cars. So that's another issue with them. So that's our advantages and disadvantages of fuel cells compared with other galvanic cells. The advantages of flow cells compared with other fuel cells are the flow cells are easily recharged by adding fresh anode and cathode electrolyte. So it almost becomes a bit more like the model of how you can go and fuel up your car at a service station by just putting more petrol in. Theoretically, you could replenish these batteries by just going to an electrolyte station and filling up with fresh electrolyte, and that would basically be a lot better than sort of having to plug your car into a power station or plug your car into a power supply and wait, hours for that battery to recharge. You've got no atmospheric emissions during the operation of a flow cell. A fuel cell is only releasing maybe water vapour, or if you're burning, say, a fuel like methanol, it will release carbon dioxide. However, you have no atmospheric emissions at all when you're operating in a flow cell. They also have a large capacity to produce electricity if you have large storage tanks. So basically, if you need lots of electricity, you can provide really, really large tanks, fuel tanks, and you can get a large ability to produce electricity. So that is the main advantages of flow cells compared with other fuel cells, and that completes our look at electrical energy as it relates to the Stage 2 chemistry course. Cheers.